Let me take my example world and apply value iteration in a quiz. And as before, assume the value is initialized as plus 100, minus 100 for the absorbing states and 0 everywhere else. And let me make the assumption that our transition probability is deterministic. That is, if I execute the east action of the state over here with probability 1, I am over here. If I assume the north action over here, probability 1, I will find myself in the same state as before. There's no uncertainty anymore. It's really important for now, just for this one quiz. I will also assume gamma equals 1, just to make things a little bit simpler. And the cost over here is minus 3 unless you reach an absorbing state. But I'd like to know, after a single backup, what's the value of A3? And the answer is 97. It's easy to see that the action east is the value maximizing action, so let's plug in east over here. Gamma equals 1. This is a single successor state of 100. So if we have 100 over here, minus the 3 that it costs us to get there, we get 97. So let's run value iteration again, and let me ask what's the value for B3, assuming that we already updated the value for A3 as shown over here. And again, making use of the observation that our state transition function is deterministic, we get 94. And the logic is the same as before. The optimal action here is going north, which we will succeed with the probability 1. Therefore, we can use the value recursively for A3 to deflect back to B3. 97 minus 3 gives 94. And finally, I would like to know what's the value of C1, the field down here, after we ran value iteration over and over again, all the way to convergence again. Gamma equals 1, state transition function is deterministic. And the answer is easily obtained if we just subtract minus 3 for each step. We get 88, 85 over here. We could also reach the same value going around here. So 85 would have been the right answer. And this will be the value function after convergence. It's beautiful to see that the value function is effectively the distance to the positive absorbing state times 3 subtracted from 100. So we have 97, 94, 91, 88, 85, and so on. This is a degenerate case. We have a deterministic state transition function. It gets more tricky to calculate for the stochastic case. Let me ask the same question for the stochastic case. So we have the same word as before, and actions have stochastic outcomes. With probability 0.8, we get the action we commanded, otherwise we get left or right. And assuming that the initial values are all 0, calculate for me for a single backup the value of A3. And this should look familiar from the previous material. It's 77. The reason is in A3 we have an 80% chance for the action go east to reach 100. With the remaining 20%, we either stay in place or go to the field down here, both of which have initial value of 0, so it gives us 0, but we have to subtract the cost of 3, and it gives us 80 minus 3 equals 77. It's also easy to verify that any of the other actions have a lower value. So for example, the value of going west will be 0 in all possible outcomes given the current value function minus 3. So the value of going west would right now be estimated as minus 3, and 77 is larger than minus 3. Therefore, we pick 77 as the action that maximizes the updated equation over here. And here's a somewhat non-trivial quiz for the state B3. Calculate the value function, assuming that we have a value function as shown over here, and all the open states have a value of assumed 0 because we're still in the beginning of our value update. What would be our very first value function for B3 that we compute based on the values shown over here? And the answer is 48.6. And obviously it's not quite as trivial as the calculation before, because there's two competing actions. We can try to go north, which gives the 77, but risks the chance of falling into the minus 100. Or we can go west as before, which gives us a much smaller chance to reach 77, but avoids the minus 100. So let's do both and see which one is better. If we go north, we have a 0.8 chance of reaching 77. There's now a 10% chance of paying minus 100, and a 10% chance of staying in the same location, which at this point has still value 0. We subtract our cost of 3, and we get 61.6 minus 10 minus 3 equals 48.6. Let's check the west action, W. We reach the 77 on with probability 0.1, with 0.8 chance we stay in the same cell, which has the value of 0, and with 0.1 chance we end up down here, which also has a value of 0. We subtract our cost of minus 3, and that gives us 7.7 minus 3 equals 4.7. So at this point, going west is vastly inferior to going north, and the reason is we already propagated a great value of 77 to the cell over here, whereas this one is still set to 0. So we will set it to 48.6. So now that we have a value backup function that we discussed in depth, the question now becomes, what's the optimal policy? And it turns out this value backup function defines the optimal policy. It's completely obvious here which action to pick, which is just the action that maximizes this expression over here. So for any state S and any value function V, we can define a policy. And that's the one that picks the action under argmax that maximizes the expression over here. For the maximization, we can safely drop gamma and Rs. So baked in the value iteration function was already an action choice that picks the best action. Here we just made it explicit. This is the way of backing up values, and once values have been backed up, this is the way to find the optimal thing to do. So I'd like to show you some value function after convergence and the corresponding policies. If we assume gamma equals 1 and our cost for the non-absorbing states equals minus 3 as before, we get the following approximate value function after convergence, and the corresponding policy looks as follows. Up here we go right until we hit the absorbing state. Over here we prefer to go north. Here we go left, and here we go north again. I left the policy open for the absorbing states because there's no action to be chosen here. This is a situation where the risk of falling into the minus 100 is balanced by the time spent going around. We have an action over here in this particular state here over here that risks with a 10% chance of falling into the minus 100, but that's preferable under the cost model of minus 3 to the action of going south. Now this all changes if we assume a cost of 0 for all the states over here, in which case the value function after convergence looks interesting, and with some thought you realize it's exactly the right one. Each value is exactly 100. And the reason is, with a cost of 0, it doesn't matter how long we move around, eventually we can guarantee in this case we reach the 100. Therefore, each value after backups will become 100. The corresponding policy is the one we discussed before. And the crucial thing here is that for this state we go south, we're willing to wait the time. For this state over here we go west, willing to wait the time so as to avoid falling to the minus 100. And all the other states resolve exactly as you would expect them to resolve, as shown over here. If we set the cost to minus 200, so each step itself is even more expensive than falling into this ditch over here, we get a value function that's strongly negative everywhere, with this being the most negative state. But more interesting is the policy. This is a situation where our agent tries to end the game as fast as possible so as not to endure the penalty of minus 200. And even over here, it jumps itself into the minus 100, still better than going north, taking the excess 200 as a penalty, and then leave the plus 100. Similarly over here, we go straight north. And over here, we go as fast as possible to the state over here. Now this is an extreme case. I don't know why it makes sense to send a penalty for life that is so negative that even negative death is worse than living, but certainly that's the result of running value iteration in this extreme case. So we learned quite a bit so far. We learned about Markov decision processes. They are fully observable with a set of states and corresponding actions, but they have stochastic action effects, characterized by a conditional probability density of P of S prime, given that we apply action A in state S. We seek to maximize a reward function that we define over states. You can equally define over states in action pairs. The objective was to maximize the expected future cumulative and discounted reward, as shown by this formula over here. The key to solving them was called value iteration, where we assigned a value to each state, There's alternative techniques that assign values to state action pairs, often called Q, but we didn't really consider this so far. We defined a recursive update rule to update V of S that was very logical after we understood that we have an action choice, but nature chooses for us the outcome of the action in a stochastic transition probability over here. And then we observed that value iteration converged, and we were able to define a policy which was simply the argmax under the value iteration expression, which I don't spell out over here. This is a beautiful framework. It's really different for planning than before because of our stochasticity of the action effects. So rather than making a single sequence of states and actions, as would be the case in deterministic planning, now we make an entire field, a so-called policy, that assigns an action to every possible state. And we compute this using a technique called value iteration that spreads value in reverse order through the field of states